Impulse and momentum. You likely have ever heard the word momentum in everyday life. We are often told that sports teams and political candidates have a lot of momentum. But in this video, we will see the word momentum has a specific meaning in physics. Thanks for watching this video, and don't forget to like, subscribe to the channel and activate the notifications. It is very important to the continuity of this channel. Sir Isaac Newton was the first person to realize that a force was needed to change the velocity of an object. He realized that the effect of a force on an object depended on its mass as well as on the amount of force. He introduced the idea of quantity of motion, in which he brings together the inertia of a body and the velocity with which it is moving. Newton defined the momentum, the quantity that Newton called quantity of motion of a body, as its mass times its velocity. In physics, the symbol for the momentum is the lowercase p. The units for momentum would be kilograms times meters per second. Newton realized that the mass and speed do seem to be linked in the sense that taken together they have an effect on inertia. Intuitively, anything that has a lot of momentum is going to be hard to stop. Let us think of two examples. An ocean liner of mass several thousand tons moving at even a very slow speed takes a lot of stopping. If it does not stop before coming to a dock, it will do an enormous amount of damage when it hits the dock. Similarly, a bullet with a mass of several grams moving with very high speed also takes a lot of stopping and can do great damage in the process of coming to rest. Momentum is a measurement of mass in motion. How much mass is in how much motion? All objects have mass, so if an object is moving, then it has momentum. It has its mass in motion. A 180 kg bumper car carrying a 70 kg driver has a constant velocity of 3 meters per second. Calculate the momentum of the car drive system. The momentum of the system is in the direction of the velocity of the system. The momentum is the product of mass and velocity. The momentum of the car driver system is 750 kilograms times meters per second. In his Principia Mathematica, Newton states his second law of motion as follows. The rate of change of linear momentum of a body is directly proportional to the impressed force acting upon it, and it takes place in the direction of the impressed force. Mathematically, we can express the second law as follows. It is easy to see that if the mass stays constant, then this version for Newton's second law reduces to the usual equation. The change of momentum is equal to the final momentum minus the initial momentum. The net force equals mass times acceleration. But now we do not care about that. We may rearrange the equation by multiplying both sides by delta t. The left side is the product of the net force times the time for which the force acts. This quantity is called the impulse of the force. The right side of this equation gives us the change in momentum. Let's rewrite everything in a nutshell. In terms of momentum, Newton's second law states that the net force acting on a body equals the rate of change of momentum of a body and takes place in the same direction. The product of net force and interaction time is called impulse. Impulse-Momentum Theorem states that the impulse is equal to the change in momentum. Calculate the average force acting on a 950 kg car when its speed changes from 5 to 30 meters per second in a time of 12 seconds. the car is moving horizontally. The problem gives the initial and final velocity, and the two velocities are in the same direction. Use the Impulse-Momentum Theorem to calculate the magnitude of the force. Suppose a ball of mass of 0.3 kilograms moving at a speed of 5 meters per second collides against a wall, returning at the same speed, but in the opposite direction, as shown in the figure below. If the ball is in contact with the wall for 0.010 seconds, find the average horizontal force that the wall exerts on the ball during the impact. The motion is purely horizontal. We will take the positive x direction to be to the right, and we know the ball was initially moving toward the left and is hit back toward the right. Thus, we converted the statements about speeds into information about velocities. We used the Impulse-Momentum Theorem to calculate the magnitude of the force. To improve the safety of motorists, modern cars are built so the front end crumples upon impact. A 1,200 kilogram car is traveling at a constant velocity of 8 meters per second. It hits a wall and comes to a complete stop in 0.25 seconds. What is the average net force exerted on the car? For the same impulse, what would be the average net force exerted on the car if it had a rigid bumper and frame that stopped the car in 0.040 seconds? To find the average net force exerted by the wall on the car, we use the Impulse-Momentum Theorem. When the car hits the wall, the final velocity of the car is 0. The net force is in the opposite direction to the initial momentum of the car, because from Newton's third law, the wall is exerting a force directed to the left on the car. In the second part, we will do the same, but we just change the time interval. The change in momentum is the same in parts 1 and 2, but the time intervals are different. So the average net force is different in both situations. The magnitude of the net force on the car with the rigid frame is more than 6 times greater than when the car crumples. Suppose that sand is poured vertically at a constant rate of 400 kilograms per second onto a horizontal conveyor belt that is moving with constant speed of 2 meters per second. Determine the force that must be applied on the belt to keep it moving at constant speed v. This is a very popular exam question and is not so hard to solve. Let us write the second Newton law in terms of momentum. In every second, 400 kilograms have fallen on the conveyor belt. So we replace mass divided by time interval with 400, and delta v is the change in sand's velocity in the horizontal direction. The conveyor belt is moving with constant speed of 2 meters per second, and that is the change in sand's velocity in the horizontal direction. This means that the rate of change of momentum of the sand is 800 meters per second squared. The force exerted on the conveyor belt by the sand is therefore 800 newtons. This force is the frictional force between the sand and the conveyor belt, and it is this force which accelerates the sand to the speed of the conveyor belt.